Okay, welcome back to another video on the Maths channel. It's your teacher, Mr. Lim here, and in this video we're going to be looking at multi-stage experiments and the product rule. By the end of this lesson, you'll be able to do these two things. Use the multiplication law. The probability of A and B is equal to the probability of A times the probability of B for independent events A and B, and recognize the symmetry of independence in simple probability situations. So let's have a look at the first part of this lesson, the multiplication law. Now, two events are independent if the outcome of one stage does not affect the probabilities of the other stage. So here in the next paragraph, I have an example of two events that are independent. For example, rolling a 5 on a die does not affect the probability of the possible outcomes when the die is rolled a second time. So the probability of rolling a 5 the first time is 1 out of 6. But if you roll a 5, it's not going to affect the probability of rolling any other number the second time. No matter what outcome it is, it's still going to be 1 out of 6 for a fair die. Therefore, rolling a die the first time is independent of rolling it the second time. However, in this next paragraph, I've got an example of two events that are not independent. So if a bag had 10 pieces of paper, each labeled with a number from 1 to 10, and two pieces were selected at random without replacement, the event of selecting the first piece affects the probability of selecting the second, as now there are only 9 pieces of paper to choose from. Therefore, these two events are not independent. Now, independent events follow the rule. The probability of A and B is equal to the probability of A times the probability of B. However, if it does not equal that, then the events A and B are not independent. Okay, so here's a general rule for multi-stage experiments if all the events are independent. Right, let's have a look at some examples. Question A. A pair of dice is thrown. What is the probability that the first throw is a double and the second throw gives a sum of at least 4? Now, we know that when we throw a pair of dice, there's going to be 36 outcomes. So it's going to be out of 36. And out of those 36 outcomes, how many are doubles? 6 of them. You can get double 1, double 2, double 3, double 4, double 5, or double 6. So that simplifies to 1 over 6. What about the probability of having a sum of at least 4? Now, instead of calculating all the ones where the sum is at least 4, it's probably easier to do 1 minus the complement of that. So, out of 1 minus the complement. So out of the 36, which ones add to 4 or add to less than 4? Well, we could get 1 and 1, that adds to 2. Or we can get 1 and 2, that adds to 3. Or we can get 2 and 1, which also adds to 3. Everything else will add to 4 or more, which is what at least 4 means. So 3 of them add to less than 4. If we were to simplify this, that will equal to 33 out of 36, which is 11 over 12. Now, these two events are independent of each other. If I throw a double the first time, the second time I throw, it's not going to affect whether I get a sum of 4 or less or more. So, because they are independent events, I'm just going to multiply these two events. So the probability of a double and a sum of at least 4 is equal to the probability of the first one times the probability of the second, which will give us 11 out of 72. Okay, what about question B? A box contains 5 discs numbered 1, 2, 3, 4, and 5. Two numbers are drawn in succession without replacement. What is the probability that both numbers are even? Well, what we need to do is we need to find a probability that the first one is even. And out of those 5 numbers, only 2 of them are even. So we've got 2 out of 5 chance of picking an even number. However, if we've picked 1 already, there's only 4 left to pick from. So let's say we've picked the number 2. Now there's only 4 numbers to choose from, and only 1 of them is even. So the probability that the second number is even is 1 out of 4. So therefore, the probability that both are even, we're just going to multiply these two together. 2 out of 5 times 1 out of 4, which is 2 out of 20, or 1 out of 10. Question C. A coin is tossed 5 times. Find the probability that every toss is a head, no toss is a head, and there is at least 1 head. Well, we know that all of these events are independent from each other. If I were to toss a coin and get a head, it's not going to affect the second time I toss it. I could still get a tail or a head, and it still has the same probability. So we want to work out the probability that every toss is a head. So head, 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 and head. Because they are all independent of each other, we can just multiply the probabilities with each other. This will give us 1 over 32. Similarly, for question 2, no toss is a head means the probability that we get a tail, 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 and tail. Which again is just going to be half times half times half times half times half, or for those of us who are lazy, half to the power of 5, which is also 1 out of 32. Part 3, however, says find a probability that there is at least 1 head. So there could be lots of different ways, but I'm not going to actually write them all out. I'm just going to write at least 1 head. What I'm going to do is I'm going to work out what the probability of getting no heads is, and then I'll just do 1 minus that. So I'm going to write 1 minus the probability of no heads, because that's the complement. Well, the probability of getting no heads is 1 out of 32. From part 2, we can see that here. And so the final answer is just 31 out of 32. All right. Question D. Wesley is sending Christmas cards to 10 friends. He has 2 cards with angels, 2 with snow, 2 with reindeer, 2 with trumpets, and 2 with Santa Claus. What is the probability that Harry and Helmet get matching cards? So the probability of the first card, there are 2 matching cards out of 10 for each of them. Okay, so out of 10 cards, 2 of them match for all of them. For the second card to match, because we've already taken 1 card, there's only 9 cards left to choose from, and only 1 of them matches. So the probability that they will get matching cards is equal to 2 out of 10 times 1 out of 9. However, because there are 5 lots of this of matching cards, right? Angels, snow, reindeer, trumpets, and Santa Claus, we actually need to times it by 5 because there are 5 chances that they can get matching cards. When we multiply that through, we will get 1/9. All right. Part 2 of this lesson is to have a look at the symmetry of independence of simple probability situations. So a coin is tossed 4 times. Find the probability that the first 3 coins are heads. So the probability that the first 3 are heads. The probability that the first one's heads is half, times the probability that the second one's a head is also half, times the probability that the third one is also head is half, times, well, it doesn't matter what the fourth one is, so I'm just going to times it by 1. So here we've got half times half times half, which is 1/8. Alright, question 2. The middle 2 coins are tails. So probability that middle 2 are tails. So it doesn't matter what the first one is. It could be heads or tails. So I'm going to just write 1 there, times the second one has to be a tail, so it has a probability of half. The third one has to be a tail, so that has a probability of half. And the last one, it doesn't matter what it is, I'm just going to times it by 1. Half times half, that's 1/4. Okay. Last question. Complete the table below knowing that a coin was tossed 4 times. So the probability that we'll get 0 heads means we must have gotten tails, 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 which is 1/2 to the power of 4, which is 1/16. Likewise, to get 4 heads, the probability of 4 heads is also going to be the same, half to the power of 4, which is also 1/16. What about getting 1 head? If we would have 1 head, that means we could get a head and then 3 tails, or a tail and then a head and then 2 tails, or 2 tails, then a head and then a tail, or 3 tails and then the last one is a head, which means there must be 4 outcomes out of the 16 where we can get 1 head. Similarly, to get 3 heads means we must have had 1 tail. So we could have gotten 1 tail here and then 3 heads, or a head and then that 1 tail and then 2 heads, or 2 heads and then that 1 tail and then a head, or 3 heads in a row and then that 1 tail, which is also 4/16. Well, there's only 1 cell left for us to complete. We can add these probabilities together and just do 1 minus that. So 5 plus 5, that's 10. So that's 6 remaining out of 16, which must be 2 heads. And so hopefully you can notice the symmetry here. We've got 1, 4, 6, 4, 1 all over 16 for this simple independent events. Right, so I hope this helps. Now you should know how to use the multiplication law, where we times the 2 probabilities for independent events A and B, and recognize the symmetry of independence in simple probability situations. Thanks.